Okay, so today we will be talking about the quantum mechanics, some rules of quantum mechanics, and also we'll explain them, of course. So, the first rule in quantum mechanics is that everything in quantum mechanics is taken as vectors. Okay, so if we talk about light, which is one of the most important concepts in quantum mechanics, the famous double slit duality of light, duality of it's called wave particle duality, or we can say duality of light. So what this over here is, actually light is made up of particles. It's both particles and wave. But if we want to explain in graphical manner, or graphical method, it's actually, this is how we would look at it. We will look at it like, because the light is made up of magnetic and electromagnetic. We call it electromagnetic field, magnetic and electric field, or electromagnetic something. So the horizontal and vertical, there's the combination of magnetic and electric field. So what we say is that we could polarize them. By polarize, I mean we could make this light, which is in both direction, which is moving in both direction towards the right, let's suppose, we could add a polarizer, a sheet of paper, which would block either one of the um, directions, either vertical or horizontal. But that depends on the type of polarizer we are using. If we are using a horizontal polarizer, what will happen is that when this light will go through this, only the vertical part of the light will be visible, and the horizontal part will be stopped. And in terms of mathematical manner, we can write it as mathematical representation will be like this. This is what we call ket. It's a Dirac notation. Dirac notation. These are one of the important concepts in quantum mechanics. So here, what actually happened is that the light, which was in both vertical and horizontal phase, just turned into only the horizontal phase, and the vertical part was stopped by the polarizer, as there is no vertical polarizer. But same would happen if we had a horizontal polarizer. Now the vertical part of the light would be stopped, and only the horizontal part would be noticed. So it will be this is how it will be represented. But here's a twist. Let's suppose we have the same example, but now when we put a horizontal polarizer at first, let's suppose, and we get a horizontal line, right? But when let's suppose now we put a vertical. Okay, before going to that like main thing over here, we will talk about what would happen if we put both. We know that if horizontal part is stopping the vertical part, this means this is 50% of the light, right? Now 50% of the light is passing through the horizontal polarizer, that means the 50% was stopped and 50% still going through. Now the vertical part, what will that do? It will stop the horizontal part now, because that's horizontal cannot go to vertical. Now what would be the result of our two polarizers? Of course it would be 0. So we could say that horizontal ket times perpendicular, which is horizontal, would equal 0. The sum would equal 0, not times, the sum. This sum would equal 0. That means none of the light went through. But if we do, now let's suppose we add a third polarizer. Here comes the main thing. When we add a third polarizer, which is at a 45-degree angle, we notice that the light which passed through was half. How is that possible? Meaning, let's suppose if this is how it's graphed, or this is the experiment. This is the light, the proper non-polarized light. It goes to the polarizer. Let's suppose the vertical polarizer. What we got? We got light of only vertical polarized. But now what you will notice is that if we put the diagonal, this one diagonal, which is at diagonals, this diagonal over here is nothing but 45-degree angle, half of the 90. In this, what we notice is the light is now brighter. But even when we add the horizontal as well, of course, at first, if this is how non-diagonal one was, and this is how the one with diagonal was, so the brightness increased when we added the third polarizer. So in graph, if this is the vertical, this is the horizontal, now this is 90-degree angle, so that means the amount of light going through is 0, because they're 90-degree angle. This one is stopped, this one is stopped. But if we take the same and we add a one which is at 45-degree angle, now the gap, this angle over here, how much is the difference? It's half, right? This half causes half of the light to pass through. It's an orthogonal. Orthogonal means what's the difference between the angle with the states. If this is the main state, this is the other state, and this is the diagonal state. So here is the main thing, that when diagonal, the 45-degree angle is added, half of the light now goes through the is seen on the back screen. This is where the screen is shown, right? Back screen. And then again, one more thing. In what was it? Wait. Yeah. So after this, okay, let's talk about uh, yeah, when we talk about the states, let's suppose right now the light is in this state, horizontal state, and when it moves forward and we put a diagonal state in front of it, diagonal polarizer, and we will take it as we have done a measurement. Okay, on this measurement, what actually happened is the system or the quantum system right now just changed. Now we have a diagonal state as well. This is what makes quantum mechanics different from classical physics, because in classical physics whatever measurements you take, it doesn't affect that system. If you make a measurement, a time of the ball falling, let's suppose the speed of the ball or distance of the ball, whatever measurement you make, that measurement is undisturbed. But in classical physics, in quantum physics, all measurement changes happen. Meaning, let me give you an example. If we have a particle which is in superposition state, we know that superposition means being in multiple states at once. And when does it happen? We know that this state can only exist when no observations are made, right? Observations are made, right? So if this is the case, right now the word observation is actually measurement. The moment you have the eyes on this system, this whole system will collapse, the wave function will collapse, wave function will collapse, sorry, collapse, and we get, sorry, we get single value. Okay, this is what happened actually. Then, and what that single value means, we have a single particle at a single point. Single, now that superposition broke, single particle at definite point. Definite point. Or coordinates, of course. So then this is what we were talking about. This is what quantum mechanics system change in quantum mechanics or the system is actually. And so then there's one more, there are many of course, and there's one more in this, which is Schrödinger equation. Okay, the Schrödinger equation over here shows the behavior, or not behavior, the evolving of the particle in a system when, since we were talking about observation, when not observed. So I thought, why not add this as well? Meaning, what is okay? If we have a particle at this point, let's suppose x and y, okay, x, y, and time, okay. So if we have this particle, again, this over here means this is an I, and there's no observation. This cross means there's no observation. So what we will observe is the change in this particle P1 or P from, let's suppose it goes from here to this place. Now this is what? Change in x-axis, change in y-axis, and t. Of course there is change in time, right? Because there are two types of equation, Schrödinger equation, time dependent and time independent. For now I'll talk about time independent, in which time is also a dependent factor. So change is done by the particle, and we don't know about this particle because we have not made any observation. And this change can be observed using Schrödinger equation. Okay, which is dt, not dt, sorry, d over t lambda, sorry, wave function minus h bar 2m. This is the equation. This equation over here is the full complete Schrödinger equation. Let me add time as well, if I have the space, of course. I think so, I have space. Okay, so this equation over here is of course is a long one. This equation is solely made for the evolving of particle in a certain space or time, a certain system. One interesting thing here is, I will say, is, let's suppose if we have this wave function, we have a wave function over here at time t, okay. So if we get information on this wave function of this wave function, we can then get the information about the future mean after it, what type of scenarios will happen, what will happen, the future wave function. The info of future wave function, future, okay. So Again, this equation is only used when there is no observations done to know what the particle is actually doing, the change in particle observed. Then there's one more rule. There's more rule. Like there's this rule about the uncertainty of the particle, meaning if particle certain property is known, the more we know about its one property, more info of one property is decreasing the preciseness on the other property. Okay, meaning if I know about its if I know about its if I know about its momentum, okay, this will cause me to know less about position, or to be exact, where it is, where it is, which is shown by this equation. This equation is the shown equation. Same goes for energy and time. Energy, time. Uncertainty. It's called uncertainty principle. Uncertainty principle. Sorry. Certainty principle. And yeah, that's it. Thank you.